Welcome back, everyone. Today we're going to take a look at an introduction to graphs, covering common graph terminology, as well as the implementation of a graph using both an adjacency matrix as well as an adjacency list. Now, if you enjoyed this content, don't forget to smash that like and subscribe button. And as a prerequisite, it's important to understand how a two-dimensional array works, as well as a singly linked list in order to understand the graph implementation methods. So if you're new to linked lists, then definitely check out my video card for singly linked lists. Cool. So graphs are very useful for modeling the relationships between data, and these can be anything from your connections in a social network, or the relationship between nodes or devices on a local area network, or even the transportation between buildings in a city. And in general, graphs are very useful and have many applications. And with that being said, let's get into it. So a graph is simply a set of vertices and its corresponding or connecting edges. So taking a look at the diagram below, each circle represents a vertex, and the red line between them represents an edge. Now, as you notice, there's also a number here, and this number is what's known as an edge weight, and it often represents the cost of traveling along that edge. So traveling along this particular edge would have an associated cost of 2, and this particular graph is what's known as a weighted graph. Now, graphs don't necessarily need to have an associated weight, and these types of graphs are known as unweighted graphs. Makes sense, right? Weighted graphs have an edge weight, and unweighted graphs have no edge weight. Now, we're going to focus on what's known as a simple unweighted graph. So we're not going to include things like self-loops, which are edges that point back to the same vertex, or parallel edges, which are two vertices that share multiple edges. So in this particular graph, we have here what is known as an unweighted undirected graph. And we will represent the edges of this undirected graph by red lines without arrowheads. Now, an undirected graph means that if there's an edge between any two vertices, you can move from that vertex to its connecting vertex and back. So we can go from 0 to 1, and we can also go from 1 to 0. Likewise, we can go from 0 to 2, and then back to vertex 0. Now, let's take a look at a directed graph, also known as a digraph. So, in a digraph, we have what are known as directed edges, meaning that we can only go in the direction of the arrowhead. So if we take a look at vertex 0, we can move it from 0 to 1, or 0 to 2. And looking at vertex 2, we can move it from 2 to 1. Now let's take a look at paths. So a path is simply a set of vertices and their connecting edges such that no edge is repeated. Therefore, a path from 0 to 4 will look like the following. Here we have a 0 to 1, 1 to 2, 2 to 3, and a 3 to 4. And a path from 2 to 5 will look like the following, where we have 2 to 3 and a 3 to 5. Now, we can also have cycles in graphs, or what are known as cycle graphs. And this means that if we start from some vertex, follow one of its paths, which again remember has no repeated edges, it will eventually lead us back to that vertex. So we have a cycle here, and we can start from any vertex within this cycle, so either 1, 2, or 3, and eventually get back to that vertex. Now, we can also have cycles with directed graphs as well, and this would be a diagram of a directed cycle graph. So here we can again start from any vertex and get back to that original vertex. However, the order we go in matters. So in this particular diagram, it means we must go in an anti-clockwise direction, starting from any of the vertices 0, 1, or 2. Here are two other examples of an undirected cycle graph and a directed cycle graph, where the cycle occurs between vertices 0, 1, and 3. Now, we're going to take a look at just 3 more terminologies for graphs, and they are acyclic, connected, and degree. Now, we've seen acyclic and connected graphs in the previous diagrams without me mentioning them, so let's go over them now. So over here we have a cycle or cyclic graph, and the cycle is between vertices 0, 1, and 3. Now, if we change the direction of the edge 3, 1, we have what's known as an acyclic graph, meaning that there are no cycles, or we simply can't start at a vertex, follow a given path, and end up back at that vertex. And here's another example of a directed acyclic graph that we've seen before. Now, as you've probably guessed, we also have undirected acyclic graphs as in the diagrams above. And again, these are just edges without arrowheads. Now let's take a look at what it means for a graph to be connected. Here we have a very familiar binary tree structure, and this by definition is a connected graph, meaning that you can start from any vertex, follow a path, and get to any other vertex. So if we pick a random vertex like 4 for example, we can go from 4 to 1, 4 to 3, 4 to 7, 4 to 0, 4 to 2, 4 to 5, and finally 4 to 6. So as mentioned before, we can basically reach any vertex from any other vertex. Now, as you've probably realized, this tree can also be labeled as a connected acyclic graph, since of course there are no cycles. Cool, the last terminology we're going to discuss is known as the Indegree and Outdegree. So let's look at what these terms mean. So if we look at vertex 0, then the number of incoming edges, or the number of edges where the arrowhead points to 0, is known as the in degree. And the number of edges coming out from index 0 is known as the out degree. So for vertex 0, we have an in degree of 1 and an out degree of 3. Cool. So we've seen some very common terminology when it comes to graphs, but this is by no means a complete list. However, it's more than enough to understand many graph algorithms. Now, moving on, as you've realized, we can't build a graph using just the circles and arrows like we've seen in the previous diagrams. So let's take a look at the ways we can represent a graph in code. So the first way we're going to look at is known as an adjacency matrix. And the second way we're going to look at is known as an adjacency list. So starting with an adjacency matrix, as the name states, we're going to use a matrix, or in particular a two-dimensional array, as a way to represent the relationships between our 6 vertices. So we have 6 vertices here, and this means we will create a 6 by 6 matrix. However, if we had 10 vertices, we would create a 10 by 10 matrix. And in general, if we have n vertices, we would create an n by n or n squared matrix. Cool. Now that we have a general idea of the structure, let's start by implementing this graph. So starting with vertex 0, we're going to go row by row such that each row number will represent our starting or source vertex, and each column number will represent the ending or destination vertex. Now, we're going to use a 0 to indicate that there is no outgoing edge between the source or row vertex and the destination vertex, and a 1 to represent that there is an outgoing edge from the source to destination vertex. So, if our starting vertex is 0, and the ending vertex is 0, then there is no edge or self-edge, so we simply add a 0. Now, from 0 to 1, there is an outgoing edge, so we'll add a 1. From 0 to 2, there is also an outgoing edge, so again we'll place a 1 there. And from 0 to 3, there's an outgoing edge, so we'll also place a 1. Now, we have no outgoing edges to vertices 4 and 5, so we'll simply place zeros there. Now, let's move on to vertex 1 or row 1. We can place all zeros here because we have no outgoing edges to any other vertices. Now, moving on to vertex 2, we again have no outgoing edges, so we'll simply add all zeros along that row. Moving on to vertex 3, we'll place zeros along the first 4 columns because we have no outgoing edges to vertices 0, 1, 2, and 3. However, we have an outgoing edge to vertex 4, so we'll add a 1 there. And because there's no outgoing edge to vertex 5, we'll add a 0 at that row and column position. Now, hopefully you get the gist of what's going on. So I encourage you to pause the video and try to finish this up by yourself as an exercise. Cool, so I hope that went well. Moving on to vertex 4, there's an outgoing edge to vertex 0, so we'll place a 1 there. And there is no outgoing edge to vertex 1, so we'll simply add a 0. Moving on, there is an outgoing edge to vertex 2, so we'll add in a 1. Now we can fill zeros for the rest of this row because we have no outgoing edges from vertex 4. Finally, let's move on to the last vertex, which is vertex 5. As you can see, we have no outgoing edges to vertices 0, 1, 2, and 3, so we'll simply add all zeros. But we have an outgoing edge to vertex 4, so we'll add a 1. And since there is no outgoing edge to vertex 5, we'll add a 0. And that's it! This is our adjacency matrix graph representation for an unweighted directed graph. Now, in the graph representation methods we're looking at, we're really concerned about the edges. But as you can see here, we're using a 6x6 matrix to represent only 7 edges. So what I want you to realize is that if we have a sparse graph, or basically a graph with many vertices but few edges, we end up wasting a lot of space unnecessarily. But if we have a dense graph, which is a graph where the edges greatly exceed the number of vertices, then the space used will be worthwhile. Now let's take a look at a simple graph where we have a maximum edge count per vertex. And as you can see, this is also an undirected graph. So for vertex 0, we'll place a 0 in row 0, column 0, since we have no outgoing edge to itself. And we'll add 1s for the remaining edges. And perform a similar approach for the remaining vertices. So for vertex 1, we have an outgoing edge to 0, 2, and 3. And for vertex 2, we have outgoing edges to 0, 1, and 3. And finally, for vertex 3, we have outgoing edges to 1, 0, and 2. Now, something that you may notice about the matrix representation for an undirected graph is that it's symmetric along the diagonal. Also, for a simple graph, all values along the diagonal will be 0, since we have no self-edges. Now, if we want to implement a weighted graph, it's as simple as using the edge weight in the place of 1s. Cool, now let's take a look at how we can actually implement an adjacency matrix. So again, as in my recent videos, I'm sticking to pseudocode that's generic enough for you to re-implement what's in here in your language of choice. Also, I will be using row and column to represent the row value and column value respectively. And whenever I'm dealing with two-dimensional matrices, I've kind of always preferred this notation as it makes it very clear as to what entry I'm referring to. Now let's get to the code. So firstly, our constructor consists of two instance variables, graph and size. Graph is going to be a two-dimensional matrix matching the size passed into the constructor, and size is simply the number of vertices in our graph. Now moving on, we have our isValidRange method, and it's used as a bit of a precautionary measure to make sure we're within bounds of the matrix. So it would return true if the row and column are valid indices or false otherwise. Now let's take a look at the addEdge method. So just like in the diagram, if the row and column are valid indices, we'll mark that entry as true. Now notice that we're using true or false to represent if an edge is there or not. Now it's also possible to reduce this space even further by using a single bit instead of true or false, and this can greatly improve the space consumption. So for example, in Java you'd use a bit set. However, for this video we'll simply stick to true or false. Now moving on to the removeEdge method, this again is pretty straightforward. We simply mark the entry as false to indicate that there's no edge between the vertices row and column. Now moving on to ContainsEdge, again this is very simple. It will return whatever value is in that entry. So if true was in that position, it will return true. And if false was in that position, it would return false. Now let's take a look at the printGraph method. Again, just as simple as the other methods. It simply loops over each entry in the matrix and prints the associated value. Now, remember how we discussed the Indegree and Outdegree of a vertex? Well, let's look at the implementation of this. In fact, I challenge you to try this on your own by observing the graph, and then we'll go over the solution. So you can pause the video here. Cool. Now moving on to the solution, the Outdegree is the number of outgoing edges from a particular vertex. And in this method, we take in as an argument the vertex or row number we want to get the Outdegree for. And then we loop over the columns along that row, keeping track of a running count. This will give us the number of outgoing edges from that vertex, just like this. Now, for the Indegree, it's the exact opposite. The vertex will be the column number, and we would loop over each row in that column. This will tell us the number of incoming edges for that particular vertex. Just like this. Pretty cool, right? Now, something to note is that every time we add a new edge to the graph, and we want to get to the Indegree and Outdegree, we'd have to perform a linear search equal to the number of vertices in the graph. So in this graph, if we have 4 vertices, labeled 0 through 3, we would perform 4 checks. And this can be unnecessarily time-consuming. So instead, let's keep a running count in a separate array. So here, we'll create two arrays, Indegree list and Outdegree list. And these arrays would store the Indegree and Outdegree for each vertex given us constant time access. This is because if we add an edge between, say, vertices 0 and 3, then we would add 1 to the Outdegree list of 0, and we'll also add 1 to the Indegree list of 3, since the edge will be outgoing from 0, but incoming to 3. Now, we'll simply adjust our add edge and remove edge methods to reflect this change. Now, notice that the remove edge method subtracts 1 from the Outdegree and Indegree, since that edge will no longer be associated with the graph. And again, don't forget that the row is the source vertex and the column is the destination vertex. And that's basically it. As you can see, implementing an adjacency matrix is mostly a matter of manipulating that matrix's entries. Now that we've seen an adjacency matrix, we've also seen a major drawback, and that is if the graph is gigantic and sparse, meaning that there are very few edges but many vertices. And in that case, we end up wasting a lot of space since the space to use is quadratic. Now, this brings us to the adjacency list representation. And this representation is perfect if we have a sparse graph, because an adjacency list is simply an array of linked lists, or sometimes a hash table of linked lists. In fact, it's very similar to the separate chaining technique that we've seen in the introduction to hash tables video. So let's take a look at it. We start off with an array of length 6 to match the 6 vertices in the graph to our left, and this will be used to identify which vertex we're looking at. So as we can see, we have one edge to 1, so we simply add a node with a value 1 to our linked list at index 0, and this represents the edge between those two vertices. And we'll add another node since there's an edge between vertices 0 and 2. And again, another node because there's an added edge for vertices 0 and 3. Now, since there are no more outgoing edges, we'll move on to the next vertex, which is 1. Since vertex 1 has no outgoing edges, we'll simply reference null or none. Now, we move on to vertex 2. And again, because vertex 2 has now outgoing edges, we'll again reference null. Cool, moving on to index 3, there's one edge from 3 to 4. So we'll add 4 to the linked list at vertex 3 or index 3. Moving on to vertex 4, there's an edge to vertex 0, so we'll add a node to our linked list there. And there's another edge to vertex 2, so we'll again add another node to our linked list. And finally, we're at 5. And as we can see, there's one outgoing edge to 4, so we'll add 4 to our linked list at index 5. And it's as simple as that. Now, let's take a quick look at representing an undirected graph with our adjacency list, and we'll speed through this one since it's very similar. So at vertex 0, we have edges 1, 2, and 3. At vertex 1, we have an edge to 0. At vertex 2, we have edges to 0 and 4. Then at vertex 3, we have edges to 0 and 4 as well. At vertex 4, we have edges to 2, 3, and 5. And finally, at vertex 5, we have an edge to 4. And that's it! Now let's go over a simple implementation of this. So I've chosen to build this from scratch, meaning that I've built an edge class that would represent a node in the linked list. I've also built an edge list class, which is synonymous with a linked list class. Finally, we'll take a look at the main class, which is an adjacency list class. And this class controls the adding and removing of edges in the edge list. So starting with the edge class, it simply represents a single edge like these in green. So we have 1, 2, 3, 4, 0, 2, and 4. Now, as I mentioned before, we also have an edge list class, and this is basically the linked list that holds all the edges for a particular vertex. This is again represented in green. So for vertex 0, we have an edge list consisting of 1, 2, and 3. For vertex 3, we have one edge in our edge list. For vertex 4, we have 2 edges in our edge list. And finally, for vertex 5, we have one edge in our edge list. Now, let's take a look at what the edge list class looks like. And here it is. Now, I'll quickly go over these methods, since they are simple linked list manipulation methods. So addEdge simply adds a new edge in constant time to the front of the linked list. Now, this is a bit different from the illustration or the diagram, but it's the same concept that applies. We're simply adding an edge to the linked list. Now, for the contains edge method, it simply loops over the entire linked list for a given vertex or index, and checks if the vertex passed in as an argument is inside of the edge list. Basically, this is just iterating over the linked list. And finally, print list simply loops over the linked list and prints the edges. Lastly, we have the remove edge method. Now, I will cover this method, but again, I am assuming that you have some knowledge of linked lists, so this should be pretty easy to follow. If you need to learn linked lists, then definitely check out my video on singly linked lists. So we initially check if the head of the edge list is null, meaning that there are no edges. If this is the case, we simply return. Secondly, we'll check if the edge we want to remove is the head of the edge list, and if it is, we'll simply update the head of the list. Now, otherwise it means that the value may be somewhere else in the list. So to help me delete the node, I've created a second reference variable called prevEdge. And I'll create another variable called edge2delete that would help me keep track of the node to delete. This will be set to head.next. Now, going to the while loop, since edge2delete is not null, we'll go into the loop. And we check if the edge's value matches the edge2delete's value. Since it does, we'll set prevEdge.next to edge2delete.next. And then we simply break out of the loop. And that's it. That's our remove edge method. Now let's take a look at the main class Adjacency List. So similar to how our edge list class contained a linked list of edges, our Adjacency List class is what contains the array of edge lists. So in our constructor, the first thing we have is an array of edge lists. This will be our graph. Then we have our Indegree list, like we've seen with the Adjacency Matrix, as well as the Outdegree list. Then we'll initialize each index in the array to an edge list with an initial value of null. Moving on to the addEdge method, it will take a source vertex and a destination vertex. And this source vertex will be used to index into the graph array, since that index will represent the vertex we are trying to add an edge to. We will then call the addEdge method from the edgeList class and pass in the destination vertex we want to add an edge to. We will then update our Indegree and Outdegree list accordingly. Now, just to be clear, basically the addEdge method in this class selects the vertex for which I want to add an edge to, and the addEdge method in our edgeList class actually adds the edge to the linked list, or basically does the work for us. Then we apply a similar process in the removeEdge method. We again take any source and destination vertex, such that the source vertex will represent the vertex we are adding an edge to, and the destination vertex will be the vertex we're pointing to. So we call the removeEdge method from the edgeList class, and again updated the Indegree and Outdegree list. Now, just like in the previous two methods, containsedEdge checks the edge list to see if it contains the destination vertex, and basically returns true or false based on the result. And finally, we have the getIndegree and the getOutDegree methods, which simply return the degree of the vertex by indexing into the appropriate array. Now, lastly, we have the printGraph method, which utilizes the printEdgeList method from the edgeList class, and applies it to all indices or vertices inside of the array. Now, looking at the time complexity, an adjacency matrix is extremely time efficient, as the addEdge, removeEdge, and containsedEdge methods take a constant time to access and update. As for the getIndegree and getOutDegree methods, if we chose to use an auxiliary array to hold the edge counts, we'll use big O of 1 or constant time, but of course at the cost of big O of v, space, where v is the number of vertices. Looking at the entire space used by the matrix, it does come at a cost of v squared. And this isn't a big deal if the graph is extremely dense, but it's definitely not a good thing if the graph is sparse, as it's a lot of wasted space. Cool. Moving on to the adjacency list, the addEdge method takes constant time since we insert at the head of the linked list. The removeEdge and containEdge methods are a bit different. These methods traverse the edge list of a particular vertex, and the number of edges will be at most v minus 1, where v is the number of vertices in the graph. Now, to see why this is, I'll throw in a quick animation after we talk about the worst case space. Now, for get Indegree and get Outdegree, it's very similar to the adjacency matrix, so it's going to have the same time and space complexity. Now, unlike an adjacency matrix where the space used is v squared, in an adjacency list, the space used is going to be big O of v plus e, where v is the size of the array, and e represents all the edges inside of the edge lists, or basically all the edges in the graph. That's how we end up with a space complexity of big O of v plus e. Now let's see why the time complexity is big O of v for remove edge and contains edge methods. So in a simple graph, meaning no self-loops or parallel edges, for a single vertex we have at most 0 edges. For 2 vertices we have at most 1 edge per vertex. For 3 vertices we have at most 2 edges per vertex. And for 4 vertices we have at most 3 edges per vertex. So basically, as you've probably guessed, the pattern here, for v vertices we have v minus 1 edges, which is why our contains edge and remove edge methods are at most big O of v.
If you enjoyed this content, please hit that like and subscribe button. See you in the next video.